So if you already did it, don't spoil it. So we have an acute triangle, and we're going to want to draw the circumcircle and then the tangents at B and C. So it's like a symmedian type configuration. Very common in a lot of problems. So here's the tangents, and they intersect at a point L. And AL is obviously a symmedian, or by the symmedian theorem. Okay. The straight line through B and parallel to AC. Okay, so we draw a couple parallels. And then we draw the line through C parallel to AB. So we see where they meet each of the tangents. So the first one, okay, so this is point B. So fortunately, they made the names easy so that I don't have to rename it. But let's see, I may want to shrink this a little bit so I get the second intersection point. There we go. We can make ABC a small triangle. So that's D, and this is E, I think. The line through B, okay, and then the line through C intersects TB at E, and then let me just make it look nicer. So, all right. So LB is equal to LC. Okay, L is a symmedian. I can make it a little bigger. The circumcircle BDC intersects AC at T. And then the circumcircle of BEC. Okay, so we're going to need to extend this. So we have this is T. And that's S. Glad I drew the figure right, because it says it's extension. Okay. We want to show ST, AL, and BC are concurrent. So AL and BC, that's where the symmedian meets BC. So yeah, another way to say it is we want to show S, F, and T are collinear. Yeah, this was actually on the exam. Looks kind of hard. Yeah, I don't even know. Do we show angle BFS as angle PFC? Does that happen? Doesn't look that easy. Yeah, we have to use the parallels. So CE is parallel to AB, and BD is parallel to AC. Oh, sorry, I missed Ruben's comment. BDC is tangent to AC. And BCE is tangent to AB. That's a good observation. So ABT is ACB. That is interesting. So then basically we kind of use power of a point. So AB squared is AT times AC, and AC squared is AB times AS. BDC is ACB. So I think AT times, I think SBTC, is that cyclic? I don't think so. No, it can't be. Oh, BDC is ABC. So yeah, BDC is ABC and BEC. Yeah, I mean, that's direct. Once we know AB is tangent, that's directly follows that BDC is ABC. All right. Let me see if we can find some more cyclic quadrilaterals. That might make this, that's not cyclic. Maybe SFDL will be cyclic, is just a guess. No. All right. So are ABC and ATS similar? I think they are. Actually, no, I don't think so. So tell me what's wrong with this? What's wrong with my logic here? So I think we would have. Let me see. So AC is tangent to this circle, right? So AC squared is AB times AS. And AB squared is AT times AC. And then if you multiply them, so I'm a little confused. So tell me where I'm going wrong here. So we would have AB squared is AT times AC, and then we would have AC. Is that correct? First of all, and then AC squared is AB times AS. Okay, so you let ST intersect BC at X. All right. So let me just delete this for now. So you're saying this is point X. X lies on the A median. And triangle BAT. A Cheva. BT is parallel to SC. Ah, I see what you're doing. So it lies on the median of triangle BAT. And so it has to lie on the median of, because it passes through the midpoints of both BT and SC. So I see why X, so if you take the midpoints of BT and SC, I see why X passes through that. But then, but by reflection, okay, because BAT is similar to BCA. Yeah, okay. All right, so that makes sense. So I think that should solve the problem. So I'm going to write it up. Okay. So yeah, first, let's see how we can show BT is parallel to SC. So I think you just did it. Oops. Okay, so first we want to show BC is tangent. The circumcircle of BDC is tangent to AC. Okay. So let me write this up. So BDC is 180 minus ACB minus BCD, which is angle ABC. Okay, so the circle BDC. Are you sure you don't mean B east? The circle. Are you sure? Are you sure you don't mean tangent to AB? Yeah, you mean tangent to AB. Yeah. All right. It's all good. And so from there, ultimately, we wanted to show that BT is parallel to SC, right? And I think you mentioned this. Oops. So ABT is ASC is ACB. ABT is ASC. How do you get that? So ABT is BCT. Okay, so yeah, okay. So ABT is ACB, which Okay, so yeah, I think I got this. So angle ABT equals angle BCT is equal to, we want to show it's ASC, right? So BCT and then ASC so this is BCA. And ASC is BSC, which is BCA. So we have so that means BT is parallel to SC. And once we know that, we can use Cheva's theorem. So AB over BS is equal to AT over TC. And of course, you don't have to use Cheva's theorem, but I mean, the proof is really easy either way. So yeah. By Cheva's theorem on triangle ASC, AF passes through the midpoints of BC and ST. I'll just say that for now. And then I'll say it this way: the line AF is the median of triangle ASC. All right. And so since ABC is similar to ASC, so that means AF is the asymedian of triangle ABC by symmetry. I'll say by reflecting over the angle bisector of A. And then by the symmedian theorem, that means AF passes through L. So yeah, we're pretty much finished here. Just So ST, BC, and AL concur at F. Did I even define F? Yeah, I should define F. Let ST intersect BC at F. I'll write that out. Just for the people watching on YouTube. But yeah, they might be like, what is F? All right, very nice. So I will move on to the next one. Okay, so we have a cyclic quadrilateral ABCD. AB is less than CD. And the diagonals intersect at F, and AD and BC intersect at E. Maybe I should, let me flip this around. Something like this instead. AB, CD. We want to see where AD, yeah, I like that better. So, whoops. Where does AD intersect BC? And then, so that's at point E. And then the diagonals intersect at F. Whoops. And K and L are the projections of F. This feels like a Burckhardt problem, right? A Burckhardt bash. AD, BC. Okay, I'll have to rename it K and L. And this is L. And M, S, and T are the midpoints of EF, CF, and DF. So everything from F. So that's M. And that's S. And this is T. And we want to show the circumcircles of MKT and MLS intersect on CD. There we go. That. I think that's the complete, yeah, I think that's the complete picture. Oops. Oh, what was K? Oh yeah, we'll draw on the altitudes. So FAD and FBC are similar triangles, and K and L correspond to one another. So that's a start. And also S and T correspond to one another. So yeah, FLS is similar to FKT. We have a lot of similar stuff here. MS is parallel to CE, and MK is parallel to BD. So we have some parallels here. Is that right? No, I'm sorry, I need to draw MT. So yeah, a homothety about F means that triangle MST is similar to ECB. Which is similar to EBA. So MST and EBA are similar. It's kind of interesting. I wonder if this is just some kind of Mikkel point idea. Maybe you don't even need Ricard. So just, let's see. Kind of like that. I don't want to make it look like AB is parallel to CD. That's the thing. But I think that's good enough. Yeah. So MKT and MLS. We want to show they intersect on CD. Let's delete that circle. I wonder if that point is the intersection of EF with CD. Try drawing it one more time. No, I don't think so. Maybe there's something else special about it. Does AP pass? No. Let's see, anything special about that point? Not that I can see of right now. Is it the midpoint? Well, that would be let's see. Let's try the midpoint. Yeah, I missed the most obvious thing. It is the midpoint. So we could draw the midpoint of CD, and then we want to show that we have the cyclic quadrilaterals. So we want to show MKTG is cyclic, and then by the same argument, MLSG would be cyclic. Interesting. Maybe we could use a homothety. So basically, if we took, like, what if we reflect F about the,
Oh, we just need angle J's.
Oh, really?
Yeah. You define that G is the midpoint of CD, right?
Mm-hmm.
So we're gonna prove that GS L and M is cyclic.
Mm-hmm.
But S L M and the midpoint of C is cyclic. That's the Euler circle, the 9-point circle.
All right. So SLM. So that's the 9-point circle of triangle FCE, right?
Yeah. And oh, you need to draw the midpoint of CE. It look like the same would be.
It almost looks like it's B in this figure, but I don't think it is. Yeah. Okay.
Yeah.
So this.
Yes.
There we go. H.
Yes. Yeah. So we need to prove the angle GSM is equal to GHM.
Okay. So GSM, yeah. We want to show is GHM.
Yeah, but GS is parallel to DB.
Yeah, because they're both midpoints.
Yeah, and SM is parallel to CE.
Mm-hmm.
So GSM is equal to DBE.
DBE. Yeah, because they're both parallels.
Yeah, and GH is equal to DE.
GH is half of DE, right? So it's KE,
Yes.
I guess, right?
Yeah, and HM is equal to CA. So the angle GHM is equal to CAE. Yeah.
So GHM is CAE.
Yeah, CAE, but CAE is and DBE is equal because the similar triangle. So we have yeah.
CAE is EBD, right? Or I'm sorry, EHE, which and then that
GHM is equal to CIE.
Okay. All right. So
Yeah.
I'm going to start writing this up. I really like that solution. Okay. So yeah, so it is all a 9-point circle thing, like you and Ruben mentioned. So, all right. Let G be the midpoint of CD. And then we're going to show that G, S, L, H, and M are cyclic. So I'll say let H be the midpoint of CE. And then S, L, B, and M lie on the 9-point circle. Hey, where'd point H go? Oh, because I just deleted the circle, that's why. So it went away. Let me just hide the circle instead of deleting it. So all right. So S, L, H, and M lie on the 9-point circle of CFE. And then, so we want to show that G also lies on it. We have GH is parallel to DE. So I'll just write out Y, AG equals GD, and CH equals HE. So that means that GH is parallel to DE. And also HM is parallel to CF. All right. So we want to show that angle GHM is GLM. So GHM is, trying to remember how we do this. Oh, and we also have GS parallel to BD. And we also have SM is parallel to CE. So we're going to try to compute angle GSM. That's the same as angle DBE. And because both those sides are parallel, and DBE is the same as CAE. All right, and CAE is GK. Trying to remember how to do this. So okay, we want to show that's GHM, right? So GHM. So GH is parallel to DE. Okay, so yeah, so that is equal to GHM. I'll clarify that since I'll just put it on a new line. So that's because AD is parallel to GH. And there's one other one too. And HM is parallel to AC. A lot of parallels here, but it works. Okay, so that means GSLHM is cyclic. And then similarly, by a similar argument, GTK is cyclic. And so the circumcircles of MKT and MLS concur on CD. All right, so I'm going to move on to the next one. So I chose 7 problems just because I felt like these were a little easier than usual. So we still have 2 more if we make it there. But yeah, I think the problems for next week are going to be harder because I chose it from a different Olympiad, or I'm choosing them from a different Olympiad. And the very last problem for this, for today, I feel like it's going to be pretty hard if we get there. So we have a triangle ABC with circumcircle omega. D lies on the arc BC. So D could be any point on that arc. We draw the tangent at B and we see where it intersects all 3 sides of the triangle. So I probably should have drawn rays. So we have this ray, and I'll draw the line BC. So we want to see where it intersects all three. So let's see, what's a good, I kind of like it better when that's on the right, like that. So you guys like obtuse triangles? I prefer acute triangles. That looks good. All right. So B, E, and F, so it intersects, oh, they call it A prime, B prime, and C prime. Okay. So this is A prime. This is B prime. And this is C prime. And then B, B prime, and C, C prime intersect at E. Whoops. And A prime intersects the circle at F. Whoops. And we want to show that B, E, and F are collinear. Looks kind of like Pascal, maybe. I'm not positive though. Right. Is that everything? Oh, I just need to draw that. There we go. So do we even use, oh yeah, we need all three, A prime, B prime, and C prime. All right. Yeah, I wonder if there's some kind of degenerate form of Pascal's theorem. Let's see. It seems like a kind of simple configuration. Maybe reframing it somehow. Like maybe we could let DF intersect BB prime at a point. I guess however we do it, we kind of have to show a collinearity, right? But yeah, we have like a complete quadrilateral here, right? Like A, B, B prime, A. And it's like, what about AC, C prime, A prime? So yeah, what's the best way to do this? Maybe projective geometry. So let's see. Maybe I could show if we project B. Maybe I could let AA prime meet BB prime at a point. And then I want to show that the two cross ratios are equal. Well, that might not work actually. I feel like cross ratios might be a kind of natural way to do this. So yeah, what if I let BD meet AA prime at a point, and then I let BB prime meet AA prime at a point. So I would want to show that if you project through point D, and I want to show that BEB prime G, that cross ratio is the same as AF A prime H. But BEB prime G, I could project it through So yeah, can I show that BEB prime G, that cross ratio, is the same as HF A prime G? It's a weird way to do it, but I don't know. It almost looks like these concur, right? Yeah, I feel like this is kind of close to solving it. Let me hide a couple things. Was it D, D, and H? Yeah, I think that's everything. Oh, basically I want to show that DG passes through this point. think that might be Pascal's. I'm just guessing stuff, right? But DG and I, maybe they meet on this circle or DG and I are collinear by Pascal's. Oh, I don't see it yet either. I'm just thinking maybe it's Pascal's. So here's kind of my thoughts. Let me write this out. So if we project through D onto omega, we have F A prime GH. That would be F D I B. And then then I want to try to calculate BEB prime G. I'm just trying to figure out what I want to project through. We could try projecting through C. Try projecting through. You know what? What if I taking B to the midpoint of arc BC? You mean like a projected transformation? Yeah, I think that should work. A prime, yeah, this is hard for me to imagine a little bit, but think. Should be a way to do it. Is A, let me check, I wonder if A prime E is parallel to IG. No, that's not necessarily true. What if I let this? Yeah, I'm just thinking if I do enough projections, FDIB, projecting through A is the same as GDIJ. Then we could try projecting through C prime. Oh, I think that might work. Because if we project through C prime, then we get B, E, B prime, G. Is that it? I think it might be that. Okay. So but I think I still need to prove one more thing. So yeah, first let me write this out, then I'll see what I need to prove. So projecting through A onto GD. Then we have FDIB is GDIJ. And then projecting through C prime onto BG. We have GDIJ is equal to GB prime EB. And so basically we have F A prime G H is that cross ratio is GB prime EB. So basically by a projection through D, I feel like that would solve it then by projection through D. So what did I use here? I used that CI and E. I used that. I used the fact that CC prime and DG meet on the circle, where G is where BB prime meets AA prime. So I'll write this. All right, see you, Kai. Thanks for joining us. Yeah, I'll send you the Discord link. So all right, and then let I equal GD intersect CC prime. And we want to, so we still need to prove so need to show I lies on omega. But once we do that, then I wonder you guys can let me know if I'm missing something here. Let J equal GI. I'll say let J equal GD intersect AB. So this is the key step right here. But once we do that, so is this E? This should be the same as E B prime E B prime G B. So then by transitivity, if since FA prime GH equals EB prime G B, then that would mean D, E, and F are collinear. So, but I just have to show this step right here. D, E, and F are collinear. But I have to show this. So I could actually hide a bunch of stuff and just try to show this for now. So yeah, what if I hide everything other than this claim? I bet it might be obvious then. Let's see what that looks like. So BB, so, whoops. This is G, and then I is GD. Oops, let me unhide I. Oh, I need C prime. Okay. So basically I need to show in this figure GD and CC prime. I want to show they meet on the circle. I can hide point E. Maybe I just went in a loop and it's just as hard as it was originally. I don't know. Could be. Is that true somehow by Pascal's, that GD and CC prime meet on the circle? Feels like it has to. Not sure how. I just changed it to a different problem. I'm not sure if the new problem is just as hard. So yeah, I don't know if like you could use the SARS or something. Maybe I could just let CC prime meet the circle at I, and then I try to show that G, D, and I are collinear. Yeah, that might not be a bad way to do it, because angle IDC, we want to show it's the same as angle GDA prime. But IDC, that's equal to ICD. It almost looks like a trilinear pole a little bit. So we have triangles A prime, B prime, C. You guys want to look at the next problem? Try this one a little bit longer.
Yeah, I think we should move to the next problem.
Yeah.
This is a kind of tough question.
Right. So here, yeah, it's weird. 2015 was like a harder year for this contest. So we have a triangle ABC, and we draw the end circle. And then I is the center. And basically, then we draw the circumcircle. And D, E, and F are the midpoints of arcs A, B, B, C, and CA. Right? So we have D, E, and F. And then we draw the parallel through I to each of the sides. So, and we see where it meets D, E, E, F, and D, F. So this point is, so they're K, L, and M. So this is K. And DF, this is L. And then this other point might be kind of far away. So let's see. Yeah, so that's off the screen. But that would be M. And we want to show that K, L, and M are collinear. There, that's not bad. Oops. All right, let me hide some things. Three, four. So I, K, I, L, and M, they're all parallel to three sides of the triangle. I don't think this actually crosses through. There's no way. But yeah. Oh, wait. Are these the polar? So, oh yeah, EF is the polar. That's right. Oh no, it's not. I was going to say, I got tricked. It looks like it passes through the tangency points, but it doesn't actually. So yeah, maybe we could use Desargues' theorem. On some other triangle. I guess I'll just draw 8 these just for the heck of it. But yeah, we need to use the parallel condition. What would happen if we used Desargues on A, B, C, and D, E, F? I wonder if that line would be like parallel to KLM. So if we drew these sides of A, B, and C, so they're parallel to those 3 lines, right? And we saw where they meet. If you consider the extension of Li, Mi, and Ki, they intersect the sides of the triangle at the same points as DE. Okay, so whoops. So I'm going to draw Li. Interesting. So that's probably pretty useful. How did you figure that out? Because of parallel lines. Okay. Oops. DF. Oh, I forgot about that fact. Yeah, so DF is the perpendicular bisector BI. Yeah, so let me draw the midpoints of AI, BI, and CI. A lot of parallelograms. Is KA tangent to the circle? Looks like it. Yeah, because KA is equal to KI. So KAI is isosceles. I think it might not be that hard to prove that KA is tangent. Feels familiar.
Yeah, KA is tangent because
An angle chase.
yeah, the angle FIK is equal to FCB, and FCB is equal to FCB is equal to FEB, FEI. Yeah.
Yeah. So basically,
KI and equal to KA,
FIK. Yeah. So FEB is FCB is FIK. So KI squared is KF times KE, but KI squared is also KA squared. So they're all tangent. It feels very familiar. Like you have the three tangents to the circle. So is there something special about line? Like maybe we could draw a line K or sort okay. So K has the same power with respect to those two. Yeah, that solves it. They all lie on that radical axis. That's really nice. I like it.
yeah.
All right.
They have the same radical axis to point E in the circle circumcircle of ABC. Yeah.
All right. So I'll just draw those three. Okay. So I'm going to write it up. So AI and D are collinear. BI and E. So are BI and E and CI and F. Well, actually, that's defined that way, so we don't even need to worry about that. So, so by the incent, so we have FA is FI and EA is EI. So that means that EF is the perpendicular bisector of AI. And so KA is equal to KI. And then we can do the angle chase. So angle FI angle FEI or FIK. And so that means triangle KFI is similar to triangle KIE. And so KF times KE equals KI squared equals KA squared. So K has the same power with respect to omega and the point circle I. Of radius 0. Whoops. And then similarly, L and M have the same power with respect to those two circles. So K, L, and M lie in the radical. Axis of those two circles, and thus are collinear. All right, it is 1:55, so we have about, or 12:55 depending on the time zone. So we have 5 minutes left, and so I'll just go back to that last problem before we finish. All right. So yeah, I don't know if I just made the problem just as hard as it was in the beginning. Might have. But yeah, it doesn't seem like a super hard problem. So I feel like maybe we're just missing something. But I'll probably figure it out after the session. Let me go back. Let me undo. I'm just being lazy here. Before I started adding in new stuff. This is what it looked like originally. Yeah, it looks like there has to, yeah, this problem can't be that hard. We must be missing something. It looks kind of like a trilinear pole because it's like we have this triangle A prime, B prime, C, and then the three extensions are collinear. So So yeah, is there another triangle? So what if we consider like the degenerate triangle DEF? So it's almost like, or what if we, All right, I think I'm going to stop here, but this will be an interesting one to try to solve after the session. So for everyone watching on YouTube, thanks for watching. So like and subscribe to my channel if you like these videos. And thanks to everyone who participated. So you all contributed a lot this session. I'll see you all next time.
Yeah.
Have a good one.
See you next time. Yeah.